Let's all go to the mall today. Okay, so we're looking here at the EMF of a moving conductor. So what's this going to look like and type of problem, and how can we go about looking at the EMF that's generated here in a moving conductor? So let's first take a look at this little demo. I'm going to create a rail. Okay, so here is a metal rail. It's some conductive rail. And we're going to say it's like square enough in shape. And we're going to say here that this has some length L. And we're going to say that there's a B field uniform around this rail and inside this rail coming out of the page. So it's a uniform B field here. Makes things nice and straightforward for us. And then let's put a kind of a floating rail right here. And what I mean by like a floating rail is it's something that, you know, there's kind of like a hole that would be run through it so that this wire could kind of like go through these holes, but it could also slide along it, okay? So this orange bar here is able to move left or right. Now, if this orange bar had some velocity to the left, what would happen here? Well, let's imagine this for a second. If it had some velocity going to the left, then in some period of time, it's going to move. It's going to move over to here, right? And this value here, this is some delta x, and it's just equal to a velocity multiplied by some amount of time, okay? It's some amount of time. We could call it a delta t. It's a change in time. Some people just rate it as t. Let's rate it as delta t, okay? Now, why would that matter? Well, let's think about the EMF that we could generate. The EMF is equal to a change in flux in some amount of time. And yes, according to Lenz's law, there's a negative here. But remember, that negative was only to give us direction. It was only to designate a right-hand rule for us. So let's just ignore it for now. Let's just look at the magnitude. And we know that this flux amount here, that change in flux, we can really think about it if we're not rotating anything, so we don't care about a dot product. It's really a B dot A, and it's just going to be BA should the dot product go away. Now, we need to change it in some way, so we either need to increase the B field. Bum-ba-dum-bum-bum. We either need to increase the B field, which we're not, it's a constant, or we can change the area, which we've actually done. If we take a look at our loop here, and these need to be closed loops for this to occur, our first loop was this. But our second loop actually includes this extra bit of area. And we know what that extra bit of area is. It is a delta x multiplied by a length. So we can say here that, you know, this B delta A over delta T, well, this is really going to be equal to a B delta X times the length over delta T. And the really neat thing about this is we can actually substitute V delta T in for delta X. So we could write this even further as saying that the EMF we're going to generate in this moving conductor is going to be B, and then the substitution of V delta T, that's the delta X, times L divided by delta T. And what we see here is that our delta T's, the amount of time it takes, cancels out and goes away. It divides away. So what we're able to say in the end of all this is that our EMF that's generated is just equal to the B field, which is uniform, multiplied by L, which is the kind of width of this wire, or the separation of that wire, the width of, or the length of the conducting floating wire, multiplied by the velocity at which it's moving in. So that's a kind of cool thing to do about that. What we also see is that this idea of having a current formed, an EMF formed in a moving conductor, also applies to like just a moving rod. If you have a let's say we've got a B field in space, so another B field uniformly in space. And then let's just have, a metal rod that is moving through the B field, right? So if we just have a metal rod moving through the B field, well, what's going to happen here? Well, as this metal rod is moving with the B field with some velocity, if we think about this, what is the force acting on the charged particles inside that rod? Well, if we look at the idea of F equals QV cross B, so some force equals Q V cross B, well, the force acting on the positive particles here would be V going to the right, B's out of the page, so I go V cross B. Oh, my shoulder's killing me. There's going to be a force acting down on the positive particles. So we could think about the positive particles moving down here, and that's right, we can't really move the positive particles. Those are the protons in the nucleus. But if that idea is held, we're also technically moving electrons up top on this conductor, which means that, hey, look, if we have a positive and a negative side here, we have just set up an EMF, okay? So we have a positive side of this and a negative side of this. So what we can kind of think of here is that if this force is acting over this distance L here, so we've got some length of this conductor that's going down, what we can say is that a force multiplied by a length, well, this is going to equal QVB multiplied by L, so QVB times L, and wait a second, this is actually really close to what we've already just seen. We know that BLV is an EMF, it's a voltage, and if we take a look at this here, we're saying a force by a length equals Q multiplied by an EMF or a voltage. We know this is work. And if this is FL, well, last year we learned this as F dot D, which is work, which this year when we talked about that for electrostatics, we saw it being QV, with the only caveat being as, hey, don't forget, our EMF is generated in the opposite direction. So, boom, we get all the way back, which is a really, really fascinating thing here. This, once again, shows us that even for a moving rod, this is the EMF for that moving rod, which is just a voltage, and we get back a work in the end of this. It took some work as that rod was moving in the B field to separate those charges in that way. So kind of a fascinating thing that we go all the way back to electrostatics with this idea of magnetic induction, but it further goes to show that, electricity and magnetism are starting to be closer and closer tied together as we know them as electromagnetism, okay? So there's two ways to get this to work. You can either have a moving rod, which will generate an EMF over the rod itself, or you could have some sort of closed loop which will run this through. Either way, your EMF generated is going to be BLV, and you could use that in all sorts of things. In our next video, we're actually going to take a look at an intergalactic problem where you're being pursued by the dangerous Lord Reztob, and you jettison some space junk, and we watch the EMF build on that. But until then, adios, and you take it easy.